All right, so welcome back to the second part of this lecture. And now we're going to talk about the ISA and microarchitecture, which is basically a dive into, again, how can we talk to the computer, right? Because again, it doesn't really understand our command because it only have ones and zero, right? So the reason behind why binary format is, if you think about it, right? What does the computer operate on? It operates on electrical signal, whether you have electrons flowing through wires or not, right? So you can actually store electron and call that a state where you have electrons. You can also just release all those electrons and get rid of all the electrons and call it's a state where there's no electrons. And you can measure it by measuring the voltage, right? So if it's high voltage, it's one state. If it's low voltage, it's another state. And you can control it, right? This is kind of like similar to your light switch at home, right? When you turn it on and turn it off. When you turn the switch on, your light bulb turns on. The room is now bright with the light from the light bulb, right? You can also turn the switch off. The room will be in a different state. It's dark, right? There's no light here in the room, right? And that same concept can work on the computer because it runs on electrical signal. It runs on electric-based circuitry, right? So you can use that to store ones and zero. And you can say ones may be a state where you have electrons and zero is a state where you don't have electrons, right? And that's convenient. That's convenient because then we can create the concept that we can represent human instruction, right, in binary format, where the commands are in binary and the data are also in binary. And you can use this assumption to interface between the assembly codes and your computer, right, and your computer. We can now use it and use what we call the ISA and the microarchitecture, right? And the gist of it is the ISA basically defines the list of commands that the microarchitecture can understand. Sounds still a little bit confusing, so let me expand on that. If you think about what is microarchitecture, microarchitecture is the hardware. Think about microarchitecture as a hardware. It's a computer circuit. All the circuitries to perform each of the command. And then the ISA is the list of all the commands that I would like to make sure my hardware can do. And the microprocessor, the CPU that you buy, the microprocessor that we know it is the combination of ISA and the microarchitecture. This allows you to interface from the software to circuits. Any questions? มีคำถามไหมครับ คำถามไหมครับ
ISA ย่อมาจากอะไรครับ
ISA ย่อมาจาก Instruction Set Architecture ขอโทษที ISA stands for Instruction Set Architecture. It defines everything that the designer, as human, right, wants the hardware to be able to do. And now let's now zoom into ISA and then think about what should be in there. What should this manual, right, be the reference book that I used as an example earlier? What should be in them, right? Obviously, you need to have instruction, right? Instruction that can give the command to the micro architecture from the programmer point of view. Programmer can issue instruction, right? The instruction would consist of things like opcode. Opcode are just the binary bits, ones and zero, that represent the operation you want to do. So it can be add, multiply, subtract, and or branch, jump, right? These are all valid opcodes for the instruction. It should have addressing mode. It should have a way to tell the data type. Is it a floating point? Is it a character? Is it an integer? It should have instruction types and format. It should have the correct formatting, right? It should it should define the format such that if you're given certain bit patterns like 11110000011, the computer knows that that's what instruction, what is the instruction is trying to convey from the program. It should also have a specification about the register and the condition code. Register, think of it as a temp variable in the program, in the assembly program. And then it has to have a definition of how it manages the memory, right? This is basically where the OS comes into play, because the OS will check with the ISA and manage things like address space. Address space is basically how I would manage data used by each program so that program number 1 cannot modify or even see the data of program number 2. Addressability, how do I go into each piece of the data? Alignment, right? How do I align each data word together? Also, things like virtual memory management is defined in the ISA. What else? Things like calls and interrupts and exception handling. If I hit the power button on my computer, what should happen? It should be defined in the ISA. If certain signal comes in, you receive a network packet, what happened? These are defined in the ISA. Access control also defined in the ISA. Can I access certain thing or not, right? How to manage priority between each program's processes, right? I have a bunch of program running. Who should have highest priority? Who should have lowest priority, right? How do I manage I/O? How do I manage the thread? How do I manage power and thermal management? These are all included in the ISA. These are something the programmer can see, programmer can modify, programmer can program, right? These are in the ISA. Now, the key difference between the ISA and microarchitecture is ISA define what software can do. ISA allow the programmer to interface the hardware. Microarchitecture is the hardware that implements the command. These are the hardware that we architect and people, the awesome people who do digital circuit, digital design, do and implement for you guys who are programming whatever things you're trying to do, whatever awesome program you're trying to make right now. It runs on the hardware. The microarchitecture is the hardware itself. These are transparent. You cannot control. These are something that we would implement based on the ISA. And these are transparent to software. You can't control how I build my hardware. But I'll make sure I build it in such a way that it maps really well with your program, right? There are many, many, many tricks, right? So in computer architecture, the majority of the work in computer architecture actually lie inside the microarchitecture, which is how do I manage the hardware such that it runs data flow. It runs as if these are data flow program, for example, through out of order scheduling. If I have multiple programs trying to use DRAM, how do I manage that? How do I predict, for example, branch prediction is something like if you have if else, right? Your CPU, right? If I have if something, your CPU will predict, is it going to the if or is it going to the else? And you actually run the future command ahead of time if it can run those things. So these are built inside the hardware, right? We call this speculative execution. We call this branch prediction. We also try to issue multiple lines of assembly in one cycle, right? These are called superscalar, right? You can also, there are also things like controlling voltage. Anyone heard about the Apple lawsuit that talks about how Apple control the performance of the processor on the phone to save the battery without the user knowing that นี่เคยได้ยินไหมครับอันนี้ เรื่องที่แบบว่า Apple iPhone แบบลด performance ถ้าแบบแบตมันเริ่มเสื่อมเพื่อจะได้ลดแบบปริมาณการใช้ไฟของ CPU แล้วแบบมีการฟ้องร้องฟ้องศาลกันประมาณหนึ่งเลย ใครเคยได้ยินอันนี้ปะครับ น่าจะประมาณ5 ปีที่แล้ว ผมจำไม่ผิด5-6 ปีก่อน ก็คือดีเทลมันก็เป็นแบบว่า เหมือนมีกลุ่ม user กับ developer กลุ่มหนึ่งมาเจอว่าเฮ้ยแบบ Apple มันลด performance ของ CPU ลงแหละ ถ้าแบตเตอรี่มันเริ่มเสื่อม เพราะว่าอะไร มีใครอยากจะให้มือถือแบตหมดกลางทางระหว่างที่ยังใช้อยู่ระหว่างวันบ้าง ไม่มี สิ่งที่ make sense ที่สุดก็คือ ผมก็ลด performance CPU ลด input voltage ลด frequency ลงนิดหน่อย เพื่อให้แบตเตอรี่มันอยู่ได้นานขึ้น สมมุติว่าเราต้องวิ่งมาราธอน22โลใช่ไหม20 กว่าโลใช่ไหมครับ ผมจะไม่สปรินต์ถ้าผมรู้ว่าผมไม่สามารถแบบวิ่งด้วยเรทเนี้ยทั้งจบมาราธอนได้อะผมก็จะไม่วิ่งด้วยเรทนั้น เพราะว่าผมรู้ว่าผมตายแน่ๆที่โลแรก ตายแน่นอนผมก็จะวิ่งด้วยเรทที่ช้าลง สิ่งที่ Apple ทำออกมา เขาเรียกว่า Dynamic Frequency Scaling ซึ่งมันเป็นเทคนิคที่แม่งทำกันทุกชิปนึกออกใช่ไหมครับทำทุกตัวผมก็งงว่าทำไมก่อนนั่นแหละมันเป็นเทคนิคคลาสสิกมากๆในฝั่ง Architecture ใช่แล้วครับ คือคือมันเป็นการลด frequency ของ CPU ลดไฟที่จ่ายเข้าไปให้ไงเพราะว่ามันไม่ได้สเกลเป็น linear คือแบตเตอรี่ที่ถูกใช้อ่ะมันไม่ได้สเกลเป็น linear ถ้าผมจำไม่ผิดมันสเกลแบบแบบ3/2อ่ะไอตัวยกกำลังมันเป็นมันไม่ใช่ linear มันเป็น polynomial เพราะฉะนั้นถ้าเราใช้เอ่อ frequency สูงขึ้น สมมุติ 20%อ่ะ มันจะกินแบตเกิน 20%จากที่เรามีอยู่ ที่เรา expect ว่ามันถ้ามัน linear มันก็อาจจะ 20%แล้วถ้าเพิ่มเป็น 30%มันก็จะเป็น 30%พอ 20%สมมุติ มันอาจจะพอมันเป็น polynomial ใช่ไหมถ้าผมเพิ่ม performance 20%ผมก็ expect ว่ากินแบต 20%โอเค งั้นผมขอลองเพิ่ม 30%มัน 30ไหมไม่ มันอาจจะไป 50มันจะกินแบตเพิ่มอีก 50%คือมันค่อนข้างเยอะมันก็เลยจะมีลอจิกเพื่อคอนโทรลพวกนี้ว่าเฮ้ยลดไฟเพื่อให้ประหยัดแบตเหมือนเวลาเราให้มือถือมัน go to sleep อย่างเงี้ยฮะคือแบบให้จอดับอะไรเงี้ยพอมันรู้ว่าจอดับพอรู้ว่า user ไม่ได้ใช้งานมันก็ลด frequency ได้ผมไม่จำเป็นต้องรันที่ frequency แบบเต็มแม็กไม่มีใครใช้มือถืออยู่ เหมือนแบบเราเข้า sleep mode ก็ได้อะไรเงี้ยครับก็ทำได้คือถ้าวงจรมันฉลาดขึ้นถึงจุดที่แบบเราดีเทคว่าแบตเตอรี่มันเสื่อมแล้วนะ มันใช้ได้ไม่ครบวันแน่ๆเราจะลด frequency มาก่อนเลยก็ได้ ซึ่งจริงๆ ถ้าผมจำไม่ผิดวิธีแก้คือ Apple ตอนนี้เขาก็ notify user แล้ว ว่าถ้าแบตเตอรี่ถึงจุดนี้เขาจะลด performance นะ ถ้าไม่อยากได้ก็จะทำให้เต็มแม็กก็เอาเลยนะครับ มันก็คือคล้ายๆกับ battery saver function ใน Android นะ So that's the dynamic voltage and frequency scaling, right? It would try to scale the voltage and frequency to save power, right? It's actually a really, really common and good trick that we do to make sure that your computer doesn't consume too much power without without the need to do so, right? So what are the ISA versus microarchitecture? So whenever you see uArch here is micro, right? Microarchitecture, design trade-off. Things like, for example, floating point 32 multiply, right? Versus TensorFloat. Anyone hear about this data point? Not data point, data type. TensorFloat 32. Anyone use a NVIDIA GPU for their research? Or does anyone here have a plan to use NVIDIA GPU or TensorFlow? All right, so long pause here.
ก็หนูรู้แค่ว่ามันเป็น tensor core อะค่ะแค่นั้น
โอเคได้เหมือนกัน so TensorFloat 32 is like NVIDIA hack on floating point 32. So it used fewer number of bits. I think from 32 bits floating point, it used, I think, 23 bits. I might be wrong here on the total number, but if I remember correctly, it's 23 bits. It doesn't allow you to go to the, so 32-bit floating point will have one sign bit, right? 8 exponent bit and 23 mantissa bit. TensorFlow 32 also have one sign bit, 8 exponent bit, but the rest would have, I think if it's 23 bits in total, right? Then you are left with 14 mantissa bit. The mantissa bit will tell you how fine grain your floating point number can be. And what do I mean by fine grain? Let me explain that in Thai. So มันคือการบอกว่าผมสมมติ floating point มันไปถึงจุดทศนิยมได้20 หลัก30 หลักอย่างงี้ไอ TensorFloat 32อ่ะมันจะไปถึงจุดทศนิยมไปไกลได้ไม่ถึงขนาดนั้นมันอาจจะไปได้แค่แบบ10 หลักแล้ว NVIDIA บอกว่าโอเคละมัน cover range เดียวกันตีต่างว่ามันเหมือนกันก็ so TensorFloat 32 is actually a design that works pretty well with things like machine learning workload because you don't need that much accuracy in terms of the number, right? You don't have to have the fine details of that floating point number in that would require 30 mantissa bits, and it works well with machine learning, right? But floating point 32 also, because it's more accurate to the true value of that number, right? So if you are working on an application that requires a lot of accuracy, then you would also still need floating point 32. So that's a design trade-off, right? That's a design trade-off. You can make an ISA that supports TF32. You can also make an ISA that does not support TF32, so you can use the transistor for something else, right? The number of register in x86 and ARM is different. It means that when you program in assembly, right, you have different number of temp variable and how you manage all this temp variable across different ISA. Things like the number of ports to the register file, right? These are microarchitecture design where I can tell that if I want to read something from the register file, can I do a parallel read? How much? How many registers can I read at once in one cycle? The microarchitecture also dictates things like if I have to do one multiply, how long does it take? Because that depends on my hardware design, right? That's my hardware design. So these two things are the ISA. These two are defined in the microarchitecture. The last two bullet points, right? The programmer doesn't have to know. The programmer doesn't even see that, but it's done in hardware. Someone make that design decision. The first two bullet points, these are what the programmer was exposed to. They can look at the number of register and they can basically use that information in the program, right? And what happened when I changed the ISA? Basically, the computer cannot understand the other ISA. Like any executable, any binary compile with any other ISA would not work. The program without source code will stop working unless you have a way to translate one ISA to another, right? And the program, even with source code, would have to be re-optimized for a new ISA, right? Compiler also have to be re-optimized for the new ISA. You can also do things like code transformation, like Rosetta on the Apple M1 and M2 chips, right? It transformed executable from one ISA into another ISA. But my key message is this. You don't want a lot of ISA, right? Think of ISA as the number of human languages, right? How many people here would agree that if human only use one language, the world might be a much easier place, to be honest. We can navigate, we could go to different country and we talk the same language. Would that be convenient? Would that be convenient? ถ้าโลกทั้งโลกทุกคนใช้ภาษาเดียวกันสะดวกกว่าไหมเราไม่ต้องนั่งเรียนอะไรภาษานู่นภาษานี้มัน so in theory, right, that seems convenient. But if you think about it the other way, some certain language is better at expressing certain things, right? There are pros and cons in all languages, right? There's certain linguistic trade-off, I guess, right? So there's also like cultural risks, to be honest. Okay, great question. So there's a question on the chat to say, is ISA a hardware or software? It's a definition of what the hardware can do. If you will, that the ISA is basically the definition of what the hardware can do and what the programmer can use the hardware for. If I want to look at it that way, is it more clear? คือมันเป็นเหมือน definition ที่บอกว่าฮาร์ดแวร์ตัวนี้มันทำอะไรได้บ้าง มันมีคำสั่งอะไรให้เราใช้บ้าง
คือมัน
ส่วนไอ้
กำหนด
ฮาร์ดแว
มา
ร์จริงครับ
อ๋อครับอ๋อขอไปครับ
เอาเลยทำได้เลย
คือผมสงสัยว่า ISA เนี่ยมันคือมันเป็นคำสั่ง แต่ว่ามันเป็น คือมันเป็นฮาร์ดแวร์หรือมันเป็นซอฟต์แวร์ที่คนเขียนขึ้นมาอะผมไม่เข้าใจเท่าไหร่
อ๋อ คือให้มอง ISA อ่ะ มันเหมือนเป็นคอนเซปต์ของฮาร์ดแวร์กัน เป็นคอนเซปต์ของฮาร์ดแวร์ว่าฮาร์ดแวร์ตัวนี้จะต้องสั่งอย่างนี้ได้ แต่ไอฮาร์ดแวร์จริงๆว่าเราจะ implement ยังไงเนี่ย อันนี้คือ Microarchitecture
อ๋อโอเคครับผมเข้าใจครับ
ISA คือชุดคำสั่ง คือชุดคำสั่งที่เรามนุษย์เราดีไซน์ขึ้นมาว่าเฮ้ยเราอยากได้ฮาร์ดแวร์อันเนี้ยที่มันแบบต้องทำอันนี้ได้แล้วก็จะเป็นแบบตำราอันหนึ่งว่าฮาร์ดแวร์ตัวนี้จะต้องทำอันนี้ได้ส่วนบริษัทที่ทำฮาร์ดแวร์จริงๆอ่ะก็จะโอเคนี่คือตำราที่ฮาร์ดแวร์เราต้องทำได้มันก็จะไปสร้างฮาร์ดแวร์ตัวนั้นขึ้นมาให้แต่จะสร้างยังไงเนี่ยก็เป็นอีกมีเทคนิคหลายแบบในการที่จะเอามาประกอบรวมกันให้กลายเป็น CPU หนึ่งตัว
อ๋อครับ คือมันเป็นแค่คอนเซปต์ใช่ไหมมันไม่ใช่วัตถุที่จับต้องได้เหมือน Microarchitecture ใช่ไหม
ถ้าคิดอย่างนั้นก็ได้ก็คือมันจะเป็นการ define ว่าไอ้ CPU หรือคอมพิวเตอร์ที่เราใช้อยู่อ่ะมันจะต้องทำอะไรได้บ้างแล้วถ้าเราจะโปรแกรมมัน ISA จะเป็นคนบอกว่าเราจะเขียนโปรแกรมยังไงคำสั่งไหน valid คำสั่งไหนไม่ valid เพราะว่าไม่อยู่ใน ISA นี้ส่งมาคอมพิวเตอร์ก็จะงงว่ามันไม่รู้ว่าคืออะไรเงี้ยครับ
โอเคครับผมครับ
ครับ All right, so basically, right, in conclusion, similar to human language, right, it's actually convenient to have one language. But again, there's trade-off in everything, right? So certain ISA might give you more register. Certain ISA might give you ability to do fancy tricks, right? Certain ISA is really, really minimal, like RISC-V, and give you not a lot of instruction to do, but then you can use the transistor for something else in the microarchitecture as well, right? So there are also trade-offs that come with each ISA. That's why you see chips built with x86, chips built with ARM processor, chip built on the RISC-V ISA, right? So these are the trade-offs. These are the trade-offs from one ISA to another. But again, at the end of the day, you're gonna see like not a lot of ISA in the world, right? Right now, there's 3 main ones: Intel x86. I mean AMD version of x86. To be honest, it's AMD version. And the ARM, right? And the RISC-V, right? And then there's also ISA that kind of govern the GPU, for example, right? But not a lot. Like it's gonna be a handful, right? And there's also a trade-off that comes with the ISA, right? Because each ISA, each language that built for the computer has the trade-off as well, right? You can look at things like how complex is each of the instruction that I have to run. How does each instruction is specified, right? How many bytes do I need for each instruction? Does it support things like low power? Does it support the smaller memory? Does it support multi-threading? Does it support SIMD? Does it support regular instruction word or VLIW? These are some of the things that you will learn, right, throughout the class. There are also different types of ISA, complex ISA, which support a lot of different instruction. There's instruction that like with one command, you would loop around to do certain thing. Or you can use reduced ISA or RISC ISA that only have the core components of what a computer need to make it programmable, right? In our lab, we'll implement a reduced instruction ISA called MIPS. MIPS is kind of like a forefather of RISC-V ISA. So we are going to build a C program that simulates MIPS instruction, right? And in terms of instruction, these are the most basic elements of the interface between the software and the hardware, right? So the main component is you have the opcode. It tells what the instruction does. It has the operand. Who do you have to perform instruction on? For example, I can issue something like add R0, R1, R2, R0, R1, R2. In this case, R0 is the operand, R1 is the operand, R2 is the operand, and the operator, the opcode, is adding. I want to add R1 and R2 together, write the result back to R0. So that's what the instruction means. It has opcode, it has operand. What else should be defined in the ISA? Sequencing model, do we use control flow or do we use data flow? So now our modern ISA use control flow. So most of the time you just look at control flow program. You run the program line by line by line by line, right? There are also attempts to build the ISA for data flow computer. It's still a little bit really complex to manage the internal hardware of the data flow computer. So most of the time, if not all, these days, modern day computing, you use control flow. There's also processing style, which basically tell you for each instruction, how many operands you can put in. You can have the zero address machine where the only 2 operations you can do. Push, pop, push number A into the stack, pop something from the stack. So these are really, really old machines. You don't see this anymore. You can have one address machine where you can put in 1 operand. Each operation you can accumulate, add up, add that number up, load and store the data into one single thing, right? The next is the 2 address ISA. These are something like x86 that we know and use a lot in the modern day CPU, right? You have two operands, add, source, destination. For example, I can do add R0 and R1, right? This is the source. This is the destination. What it means is what I would do is I'll add R0 plus R1, and I will write this into my destination, R1. So add R0, R1 in x86 will mean that I'm going to add R0 and R1 together, write it back to R1. So that's what the two operand machine is. It's a little bit limited. It's a little bit limited, but it also saves the space on the instruction. So instruction is going to be that big when you are using the two address machine. You can also have three address machine where you have two inputs and one output. So this one has a better support into having two inputs, one output, right? This make a little bit more sense when you look at like multiply and add and like instruction that requires two inputs. So if I do add 0, R1, R2 over here, it basically means I'm going to add R1 and R2 together, right? And write the result into R0. What are the trade-offs here? How big is the code that you're writing? The space trade-off, the code size, the performance, right? How fast it is. So a three address machine, it might consume larger code size, right? Because you have to specify source 1, source 2, and destination. But then it might perform a little bit better per operation, right? It depends on how you implement this. It's giving the hardware more room to optimize your hardware design. Also, things like number of executed operations, because the 0 or 1 address machine, you are likely to require a lot of push, pop, in order to make any sense of the program, right? Then what else are the elemental arrays? We talk about opcode, we talk about operand, right? Now we also have things like operand specifier. How do I go and get, right, and get the address? You also look at things like data type. What does the bit represent? Is it integer? Is it floating point? Is it character? Is it binary? Or is it a complex structure, right? For CISC, I said complex, I said like x86 or even a full-blown complex, I say like wax. We don't use wax anymore. There's no machine that use wax, I say anymore. But back in the day, wax is like the end of the cis versus red spectrum. Like it have, there's likely an instruction for whatever you're trying to find. x86 is also a CISC ISA, which might support a complex structure other than integer, floating point, character, binary, right? Also the ISA would dictate how complex my instruction can be, right? Can I have an instruction that say computer convolution or load an entire array into my register, right? Some of these are pre-built into CISC ISA, right? Or does it support simple instruction only, like add, XOR, load, store, right? Complex instruction, again, can't always be built from simple instruction. That's why RISC ISA, like RISC-V, also works, and it can be implemented. Any program can be implemented in RISC-V ISA. So the trade-off is what? If you have complex instruction, you're likely to have a much smaller code, right? Your compile binary is going to be smaller because that's one instruction for everything. So instead of having to spend 100 assembly lines to implement a loop, you need one instruction that would loop around and do certain thing, right? The compiler is going to be simpler because it doesn't have to map a lot of small instruction to perform one complex task. There's likely an instruction for that. For the reduced instruction, it simplifies the hardware, which means that I can only just build something to perform simple instruction, which also means that I can clock, it's likely that I can clock the CPU higher and likely that I can squeeze out performance out of the CPU. But it also requires compiler optimization because compiler can do a lot of additional tricks on the assembly to make sure that it's more optimized based on the hardware specification, right? And now we are talking about instruction complexity trade-off. We also have to touch on the topic of semantic gap. Semantic gap basically means that it's the gap between your program, the C code, Python code that you're writing, to the ISA, to the assembly that you compile, right? So this is the program that you're writing, and this is the compile code, right? Over here is the semantic gap. If you have an ISA with a large semantic gap, means that your instruction is really low level, it's close to the hardware, right? Instruction might be like a set of control signal, and then the compiler, right, will generate instruction to control each of the wires and things like that, right? This allows more compiler optimization, but also more headache on the compiler side of things, right? You can have ISA with small semantic gap, means that the ISA specification would look like a high-level language like Python or C, right? This allows more application-specific hardware optimization, but also headache on the hardware designer, because now we have to implement a lot of function calls, right? And translation from one ISA to another ISA is essentially changing the semantic gap. And this can be done either in hardware or software, right? So that's a semantic gap trade-off. That's also trade-off in different data types. For example, right? If I can support a high-level data type like a linked list in the ISA, it sounds good, right? But the benefit is I can have that strict data type support. I don't need a lot more instruction to handle a linked list, a hash table, for example, right? But the downside is you now have to implement those things in hardware. And this put an effect to the semantic gap because the data type tie to the semantic level, right? What else are the elements of the ISA? Things like memory organization, right? Address space, how many unique locations in the memory that is defined for different tasks in a computer. Addressability, can I access each byte? Can I access each bit? Can I only access a block of 64 bits or a block of 32 bits? For example, if you have to add two 32-bit numbers together with a byte addressable machine, how do you do that? And if you have to do adding two 8-bit number with a 32-bit addressability, how do you do that? Because the first case, you need to add two 32-bit number. That's 4 bytes, but you can only get 1 byte at a time. How do you do that? How do you add 8-bit number, but every time you try to access that number, you get the whole 32-bit block, which is 4 bytes, right? These dictates how you would write your program as well, whether it support virtual memory or not, or does it support big endian or little endian or both, right? What else? How many register do we have in the ISA? You can think of register as a really, really, really fast temp memory, like a temp variable in the program, right? So the more we have, it seems more convenient, right? So it makes sense that we have a lot of register, but this thing also costs a bunch of transistor as well, right? So the benefit is definitely I can use this temp storage to store frequently used data, right? And you can get data locality, and we will talk about this, what it means in the caching lecture. We're not gonna talk about data locality right now. But the number of register and also the size of each register impacts how you program. It impacts how you program. And then for the, like, I guess, historical reason, I want to also show a quick overview of the evolution register. Back in the day, you can't store a number. You would start with an accumulator. You add like add one to the register, right? Then you can have the accumulator, like add one, but then you can also have another register that store the address where in the memory is the data located at. But nowadays, we have general purpose register. Nowadays, every single ISA would have general purpose register where you can use this for any purposes. It's easy to use, easy to manipulate, and it can range from a few register to even 128 in the Intel IA64. Intel attempt to propose the 64-bit x86, right? And what else? We can talk about addressing mode. How do we obtain the operand? For example, you can have support. You can have support for the absolute addressing mode, like load R0 10, which basically means that I'm gonna load address 10 into R0. I can use register indirect, which means that I'm gonna go to address where R1 is, and then I load it to R0. I can use displays or base where you have offset R1, means that I add offset to the value of R1 that becomes my address. And I'll check that address. What's the value in there? I load the value into R0, right? So each ISA would also now define its own addressing mode. For example, RISC-V ISA would support different types of addressing mode. And in that book, in that ISA manual, it would tell you how do you use each of this? Basically, these are all design choice. You can use it or you can not use it, right? And each ISA would have a manual comes with it that tells how do you use it, right? Then there's also how do you interface with the I/O? Do you support memory map I/O where each memory region is mapped to certain I/O device? For example, these regions map to the monitor, this region is mapped to the network card, and if you have things coming in, it would be written here. Does it support special I/O instruction where it deals with I/O device, right? Privilege mode, tell who can run what, right? How do you handle exception and interrupts? What are the procedures to follow when something goes wrong, right? What are the procedures to follow when, say, external device, like someone type on the keyboard? How do you handle that? Do you use vector interrupts or non-vector interrupts, right? How do you use virtual memory? How do you use access protection, right? The instruction itself also have 3 different classes. Compute. Compute means it's simple, like add, subtract, like you process the operand, right? Data movement, it means that I move something to the memory or I take something from the memory to the processor. And then control flow. Control flow is jumping and branching. You instead of going to the next line of your code, instead of going to the next line of your code, you go somewhere else. When you have if else or for loop, it requires control flow instruction for that. The way you interface with the memory also have the trade-off. You can use a load store architecture where instruction operate directly just on the register. You can't go to the memory and do the add and say, I want to add this memory address to this memory address. You have to do it to a load or a store. You put the value from the memory to the CPU first. So the load store architecture, basically think of it this way. You have CPU, you have the memory. And if your CPU want to do something, you have to load or store to the CPU first. Many of the RISC ISA support load store architecture. Many CISC ISA also support memory-to-memory architecture, where if I want to do an add, right, I can send the add instruction to the memory, and the memory to memory location would get added. And you can command it from the ISA, right? there are also trade-off with this, because if you want to do a memory-to-memory architecture, you need to build more hardware to support that. Load store architecture is actually simpler and cleaner. Actually, modern day sys ISA, like, go with the load store architecture more often than you think, to be honest, right? There's also instruction length trade-off. You can have fixed length where each instruction is X number of bytes. For example, I can assume that each instruction is 4 bytes. Every single instruction is going to be 4 bytes. This is easier to decode. Sorry about the typo. I have this every single semester and I haven't noticed that I have the typo here every time I go through my slides. It's easier to decode, right? It's easy to decode multiple instructions at the same time, because I know that every single instruction is 4 bytes. So it means that if I want to decode 10 instructions at a time, I just bring in 40 bytes and I split them into 4 bytes, 4 bytes, 4 bytes, 4 bytes, 4 bytes. And then I know that those are all my instructions, right? The downside is you can waste bit, because sometimes you don't need the entire 4 bytes for your instruction, right? It's also hard to extend. For example, you want to add more instruction, right? Sometimes you run out of bits. And one example of the fixed length instruction is the RISC-V ISA. The integer-based instruction format would support either 32 bits or 16 bits, right? So you know exactly how many bits you have to read from the memory to get the integer instruction, right? You can have a variable length where you see already from our sample code in part 1 from x86, right? This is compact encoding. You can have instruction with 1 byte. You can have instruction with 7 bytes as well. It's harder to decode, right? It's harder to decode because you have to tell how long the instruction is. And the example is for x86, where, for example, the same instruction, VEX, right? There's a 2 bytes version and the 3 bytes version, and you can only tell what version is that after you read the first byte, because there's only 1 bit different right here, right? So when you have to decode, basically decoding means I try to figure out this bit pattern, 1s and 0. What is this instruction? That's a trade-off, because variable length takes more time to decode. There's also decoding trade-off where uniform decode means that the same position means the same thing. This is easier to decode because it's much easier to design the hardware, right? Also can waste instruction space. You can have non-uniform decode where things are more compact, easier to extend, right? But each position of the bits can now mean different things. So it's much more complex to build the hardware to figure out what are the commands. All right. Any question มีคำถามไหมครับ Any question before we move on to the next topic, which is single cycle architecture? นี่ผม
ฮัลโหล
ผม
ครับ
ยังครับ
อาจารย์อธิบายหน้า 43 ได้ไหมครับ
หน้า 43 ได้เลยครับ
คือไอ้รูปเนี่ยมันคืออะไรล่ะครับ
อ๋อ ไอ้รูปนี้คือตัวอย่างของ ISA ที่เราจะบอกว่าทุกคำสั่งมันจะมีขนาดเท่ากัน คือ ISA เนี่ยมันมีได้หลายแบบมากๆเลย เพราะว่าจริงๆ คนที่กำหนด ISA คือมนุษย์ใช่ไหม คือเราอาจจะดีไซน์ว่า ISA เราอะทุกคำสั่งมีขนาดเท่ากัน คืออย่างตัวอย่างเนี้ยคือใน RISC-V processor อะมันจะเป็น ISA มีขนาด 4 ไบต์ 4 ไบต์ 32 บิต เพราะฉะนั้นทุกคำสั่งของผมอะจะมีขนาด 4 ไบต์หมดเลย แล้วตัวอย่างที่ผมเห็นในตารางเนี้ยก็คือจะบอกว่าถ้ามันต้องซัพพอร์ตแบบ register 3 ตัวแบบปกติอย่างเงี้ยตรงนี้ก็จะเป็น op code แล้วเราก็จะเห็นว่ามีขนาดเท่ากับ 32 บิต ก็คือ 4 ไบต์ แล้วก็แต่ละ position ก็จะทำงานแบบอันนี้เป็นฝั่ง source ตัวแรก source ตัวที่ 2 RD ก็คือแบบเราเอา source 1 บวก source 2 แล้วใส่เข้าไปใน RD อะไรเงี้ยครับ แต่มันก็จะมีหลายๆ format อย่างเช่น ถ้าเป็น op code แบบนี้มันต้องรับ register 4 ตัวที่ 1 ตัวที่ 2 ตัวที่ 3 ตัวที่ 4 อย่างเงี้ยมันก็ทำได้แล้วมันก็จะบอกว่าแต่ละ position ของบิตพวกเนี้ยมันคือสำหรับอะไรบ้างแล้วอย่างฟังก์3ฟังก์7เงี้ยครับถ้าเราไปเปิดในคู่มือมันจะบอกว่าฟังก์3ตรงเนี้ยเป็นบิตอะไรได้บ้างแล้วแต่การที่บิตตัวนี้เป็น0หรือเป็น1อ่ะมันมีหน้าที่อะไรคือในคู่มือใน ISA มันจะบอกหมดทุกอย่างเลยแต่ว่า point ของอันเนี้ยก็คือว่าทุกคำสั่งมันขนาด4 ไบต์คือ32 บิตหมดเลยนะครับแค่นั้นเลย
ขอบคุณครับ
ครับมีคำถามอื่นอีกไหมครับนั่นแหละก็คือสรุปคร่าวๆนะครับ ISA มันก็คือสิ่งที่มนุษย์สร้างขึ้นเพื่อบอกว่าคอมพิวเตอร์จะทำอะไรได้บ้าง แล้วก็คำสั่งเนี้ยมันจะทำงานยังไง มันจะมีขนาดเท่าไหร่กี่ไบต์ต้องอ่านกี่ไบต์ที่บิตนี้มันจะเป็นตัวบอกว่าอันนี้คือ register ตัวไหน หรือว่าบิตนี้มันจะบอกว่าอันนี้คือคำสั่งบวกลบคูณหารหรือเปล่า คือเราจะอ่านจากไอตัว ISA หมดเลย มันจะเป็นคนกำหนดทุกอย่างนะครับเท่านั้นเอง All right, so that's kind of like the overview of the second part of this lecture. So let's do a quick pause again before we transition to the third part. And for the third part, I want to give you enough overview so that you can start doing the first homework, the first lab, basically. And then we'll kind of talk about the lab a little bit in the last maybe 15 minutes of this lecture. All right. Okay, so let me stop the recording so we have the second clip for this lecture.